Hi, I'm Yue from the University of Tokyo. In this study, we propose bidirectional contrastive split learning for robust decentralized visual question answering. Multimodal machine learning has been extensively researched to comprehend information across different modalities. Visual question answering entails answering natural language questions by analyzing the contents of a presented image. For example, one presented with an image along with the question, "Where is the bag?" A model is expected to generate the answer on the table. Conventional approaches to large-scale multimodal machine learning, such as visual question answering problems, involve creating a centralized dataset from different users for model training. Then the trained model is used for inference. Limited attention has been given to improving privacy and robustness in multimodal learning. One solution is decentralized machine learning, achieved through collaborative learning among diverse local models, relying on the sharing of learned client model weights. The transfer and aggregation of knowledge from these individually trained models are crucial for attaining the training objective for the entire data distribution. As shown in this table, approaches to multimodal learning typically adopt a monolithic structure, utilizing a single fusion model and requiring both data and model sharing. In the graph on the right-hand side, the MNIT is a decentralized approach to improve the model performance without the need of disclosing the training data. However, there are two issues with this structure. Firstly, while MNIT does not necessitate the sharing of task data, it does require the sharing of the entire training model. This increases its vulnerability to adversary attacks such as model poisoning. Secondly, the efficiency of large-scale model training on local devices is usually hindered by the computational constraints of these local devices. To address these issues, split learning was proposed, which divides a model into three components: a global component FG, and two client components FC1 and FC2 here. Then to utilize the interactive activation and gradient exchanges between the server and the clients for the decentralized learning. So here it utilized a unidirectional process where all the activations shown in the read lines are sent through a forward path from FC1 to FG and finally to the FC2. And the gradients, on the other hand, are computed through an inverse path from FC2 to FG and to the FC1 finally. However, the sequential processing of these components, as you can see, it can result in longer waiting time, since the components need to first finish the previous component's computation every time. By control, we aim to introduce a framework called the Bidirectional Contrastive Split Learning, or BiCSL for short, that enables the concurrent processing of model components based on the contrastive learning. It utilizes the bidirectional process instead, where the activations are sent through the path from FC1 to FG1 and also from FC2 to FG2. And all the gradients are computed with an inverse path sent through from the server to the clients. As a result, the activations and gradients of these local components can be computed concurrently without the need to wait for the computation of the previous components, which is the case in the sequential learning in the split learning. To this end, we propose the bidirectional contrastive split learning, a framework that decouples multimodal model into representation modules and a contrastive module for gradients and weight sharing. It consists of three main components: an answer projection network, or APN for short, for the semantic understanding of the answer input. And there also a multi-header attention, which is the main part inside the visual question answering module, taking inputs of the question and the image. And finally, there's two adapter networks at the server side, LTA and NHA, to perform the contrastive learning to align different modality representations. We later will show the existing VQA detectors can be applied efficiently by simply replacing the multi-header attention part. And we can also employ the weight sharing strategy on both the client and the server side learning. This enables the framework to learn the entire data distribution across different clients' local data through the weight sharing. This architecture does not require clients to disclose either their data or the complete model architectures. Contrastive learning aims to disentangle the similar and dissimilar parts of the data inputs. In particular, within one batch, given the output of the NHA or VNHA, the embedding, we use the paired LTA output. When the J is equal to I as a positive pairs, and any other irrelevant LTA outputs when the J is not equal to I as a negative pairs, then we want to align the representations between the different input modalities. The alignment of the two components LTA and NHA is achieved through the use of the contrastive loss. As illustrated in the graph at the bottom right, after the training, the diagonal part representing the paired vectors exhibits significant higher similarity, where similarity with other negative pairs is disencouraged. So that for a given image and the correction pairs embedding, based on the similarity, the embedding of the correct answer can be retrieved. Then at every epoch, weight sharing is applied to these different components, including the client-side APN, MHA, and the server-side LTA, NHA. The averaging of the model updates from different clients is computed and used as the aggregation result. Here I show the evaluation results based on the VQA V2 dataset. During the training, the set was randomly divided into two non-overlapping subsets, serving as the local datasets for two clients. We assume the two clients share the same model components, but cannot share data due to the privacy concerns. And we compare the centralized VQA model, which is contrastive learning here, and with the proposed BiCSL method, which is decentralized method. The result from the 7 state-of-the-art VQA models demonstrate the applicability of the BiCSL to different VQA models, allowing the training of a model with similar capability to a centralized model, while ensuring the protection of the data and the model privacy. The proposed BiCSL also exhibited a stronger robustness against the Trojan attacks. To assess its robustness, we conducted a dual-key backdoor attack. In this attack, the perturbations are introduced into the images, along with the malicious tokens added to the end of the correction. Then the combined multi-modal Trojans aims to compromise the VQA model so that it will produce the incorrect answer. As shown in this sample here, we added some noise into the image inputs and also manipulated the last word in the correction. Then the answer becomes an incorrect one. Finally, this figure illustrates the task performance under Trojan attacks. The BiCSL demonstrated significantly much better robustness. And the two possible explanations could be the self-supervised learning increased the difficulty of generating effective Trojans, and the decentralized learning that avoids the entire model sharing also decreases the attack success rate. To conclude, we propose the bidirectional contrastive split learning to address the decentralized learning of multimodal learning, and the BiCSL can achieve competitive performance compared to a centralized method, while ensuring the privacy protection and robustness against adversary attacks. For future research, the approaches like the differential privacy can be used to secure the activation and gradient sharing between modules. And we also aim to extend the BiCSL framework for online continuing learning studies. We hope this work will motivate more research in decentralized multimodal learning for robust real-world applications. Please refer to our paper for more details. Thank you.